So what do you propose after this little thought experiment? What do you propose that we assign the value of this monster? I hear 2. By experiment, by kind of empirically trying this and just testing, it does feel like the answer should be maybe 2. Do you agree with Max? Yeah.
I pointed the interval, but my big limit was a 1 with many zeros after it.
Good.
And my calculator gave me 0.
And you went from 0 to
So a big number.
a big number? I think you may have just like broken your calculator is all I don't know. But it seems like that should work. I don't know. I'd be interested to look at what you have on your calculator. Make sure it's typed in right and all that. But it's possible that like you overload your calculator with asking it to do too much or something. I don't know. All right, so let me do this first one with you. This is on the sheet there. We'll be going through this. It's kind of just the problems are on the sheet. I don't know why we have like a note sheet here, but we do. They're not that hard to write down. But so this is the first one we're looking at. So it feels like the answer should be 2, but is there a way to arrive at that without having to like resort to just testing it on the calculator or using that? And the answer is yeah, we can use limits. So here's this calculation. Just like when, I don't know, do you remember doing some infinite sums back in pre-calculus? Whenever you had a summation notation with an infinity on top, we really just said, oh, look, well, we can handle that. That's just the limit as m goes to infinity of the sum from whatever to m, right? So we can understand how that's done. And remember that an integral is just a sum. That's all it is. That's all it is. So we can do that same trick here. So even though this might be, at this moment, a little bit ill-defined in your mind, we can just redefine it to be really just this, right? We just mean, let's go to, and isn't that the process you were just taking? Didn't it feel, weren't you feeling like you were doing a limit as you were doing this? You were increasing the upper bound on that integral, making it go toward infinity. So let's actually symbolically do that. So I had this limit as a goes to infinity. There's nothing special about the letter a. I just chose it as a dummy variable. That just hangs out front while I do the normal integration. This is something, by the way, right? We can integrate e to the negative x over 2. That's the antiderivative. Evaluate that from 0 to what? Well, how about just a as a dummy variable? Again, keep in mind that this limit as a goes to infinity is just hanging out front. And so this is the expression we're dealing with. Do you know how to take the limit of that as a goes to infinity? Well, this part doesn't involve a, just 2, right? And this part goes to what as a goes to infinity in this expression? If a is something really big, this part goes to 0, right? So now we've proven in a more rigorous way than just kind of like randomly trying upper limits on the calculator that this is 2. And this is the kind of work we expect out of these problems today. Okay. And now it's just, let's try a few problems, and we'll also along the way present another, kind of maybe 2 other snags as well. Okay. It's certainly true that when you get to this limit stage, this could be not defined, right? Can you give me an integral that you know diverges? It depends on the, let's talk about on the interval, I don't know, 0 to infinity again, say. Can you give me an integral that you know diverges? That's a little bit weird because that one does go downhill. I think we might be right, but we can't integrate that. You know, if the 0 to infinity is a weird one to do there. What's like a, don't go too crazy on me here. I mean, just what's a very obvious one that if you were to try to integrate something from 0 to infinity that you would get an answer that's definitely not a constant? Yeah, x squared. Like, what's the area under x squared as we go up to infinity? It diverges very quickly. It's not headed towards some number. So, and we'll see some that maybe diverge today. When you get to this limit stage, the answer might be, you know, infinity or undefined or something. But here we have the integral converges to 2. So let's do another one here. This requires along the way that we remember our integration techniques. So that's not the main focus. So I don't know. Anyone want to give a spoiler? Well, this time let's rewrite the limit first, and then I'll ask you if someone has the antiderivative for us. So how are we rewriting this? We're rewriting this with a limit as, what's your favorite letter? You can use a, sure. As a goes to this time maybe negative infinity. And then now I'm ready, I think, to hear from someone who has an antiderivative for us for that guy. Not too bad, right? Yeah, actually, maybe that is a little bit bad. Maybe we should stop and do this integral all out here. This requires a small u substitution. Let me. Let's rewrite this as if we pull out, maybe we could go ahead and write it right away in terms of u. But if I write this as now I need a, what did I just pull out? A 4 on the bottom. So what do I have out front here? I need like a 1/2 in here. Or 1, right? Because the 2 and the 4. Is that still the same thing? Multiply that all and make sure that I have that right. Is that still the same integral? I didn't mean to change it. It's still the same, right? Call this a 2/4 if you like, right? 1/2 is 2/4. The 2 gets to the top, the 4 goes to the bottom, and we get that. Yeah. Why did I do that? What's the antiderivative? Does someone have it now? It's not ln of anything. It's what? Yeah, good. Okay, I just hadn't heard someone say that yet. You can put the 1/2 wherever you like. But yeah, this is the inverse tangent of x over 2. Let's think about this a little bit more here too. And the derivative of that will be 1 over x over 2 squared plus 1 times 1/2. So maybe we have that then, right? The 1/2 is taken care of. And they check us on that, right? Does that work? Check the derivative. I just did mentally, and I think it works. Chain rule as well, right? So 1 over x over 2 squared plus 1, and then times 1/2. That's exactly what we have up here. So I think we're good. All right. Well, maybe the limit is the easy part. I don't know. So what do we have? Tan inverse of 1 minus tan inverse of A. What's the tan inverse of 1? That's not, there's no limit to speak of here on this part. That's just a number, and that's what? Say it confidently. Pi over 4. And what's the limit as the inverse tangent of A approaches, infinity to that expression? My go-to on this would maybe be visual, like to look at the graph of the inverse tangent function, if you like. What do you get? What's the inverse tangent of infinity? How do you get a tangent of infinity for an angle? What angle do you have to be very near to get a tangent of infinity? You can go back to geometry class, right? How do you draw, what angle do you have to put in a right triangle to get a tangent of 1,000,000? Not pi, you can't put a pi in a right triangle. Pi over 2, right? Now you need something very close to 90 degrees. Okay, so there are a couple different angles on how you come in on this. You can also think of, if you know the inverse tangent graph, where is that asymptote? On the right, on the left side. I guess we're heading toward negative infinity. And the answer is negative pi over 2, right? So yeah, negative pi over 2 and pi over 2 are those two horizontal asymptotes on the inverse tangent function. So what is it, 3 pi over 4? We're integrating all the way out to infinity here on one side, yeah.
So does the 1/2 just not matter?
So this 1/2 got kind of sucked up into this integral. I did a u substitution kind of on the fly. Just take the derivative with me, walk through it real carefully again with me. If I'm checking the derivative to see whether my integral is right, it's 1 over x over 2 squared plus 1. Oh wait, times a half by the chain rule.
Okay, so the half
So,
that's in
yeah, so this got accounted for as we did the u substitution. So in some sense, us having a 2 up here, because that's us like doing you a favor, right, in the problem. It actually really worked out nicely. Because like the appropriate constant was already like there waiting for us. Feel free to slow down and like do the whole u substitution off to the side. I just didn't want that to be the main focus, but you know, just do go in back and review those techniques if you need to. How are we going to handle this situation? It says evaluate or show that it diverges, whichever. Yeah, those will be our instructions. Because either at the end, this limit will be something nice, like we got here. This is perfectly right. Or it could be that it diverges. But we're not going to tell you ahead of time. Just see what happens. Either find the answer or say that it diverges, right, is the instruction on all of these. So I don't know, some of these might. Oh, this one's not bad here. That antiderivative we're already excited about as much as you did in the last one. What's the snag here? Well, we have negative infinity on both sides here. So let's I don't know, let's break it up into 2 integrals maybe. So we get negative infinity to 0, or whatever your favorite number is, somewhere in between negative infinity and infinity. And now we've reduced it to problems of the type that we've just been doing. Right? If you want to use separate letters, you can. You can use A again in both cases if you like, though. We just want to say inverse tangent here. So I just want to, this is not meant to be too much harder than the last one. These integrals, these limits are all similar to the last ones here. So we'll just say, we get what? We get tan inverse of 0 minus tan inverse of A, taking the limit as A goes to infinity of all this. Negative infinity, excuse me. What do we have over here? Tan inverse A minus tan inverse 0. What's the tan inverse of 0 in both cases? 0, right? What's the tan inverse? We just did this, right, a second ago, so just recall from our thought experiment previously. What happens as we go, what do we get here, as we head toward negative infinity on the inverse tangent? What did we say? We just did this one in the last problem. Yeah, negative pi on 2. And over here, what's the horizontal asymptote on the right of inverse tangent? Positive pi over 2. So in the end, we get, what do we get? You want to be careful with the signs. We get pi. Zero, just think about the geometry of the situation too. This is an even function. We're going to get the same area on the left as on the right. We can add them up. We get pi over 2, pi over 2. We get pi. This is an even function. Looks like that. Improper only just refers to the fact that there's some infinity involved, right, in the limits. Or in some other way that we'll talk about in a second here too. It should be remarkable that pi has anything to do with this rational function. This would be fun to go back and tell your pre-calculus friends, right? We got 1 over x squared plus 1. In pre-calculus, you might have done that. It's a nice rational function. The area under that, from negative to positive infinity, is pi. Wow, that's cool. Yeah, sorry. It should be a over 2, but it doesn't matter. Because it's infinity. This one I think is out of order on your sheet. Let's do this one first though. 1 over x, I think we get this, whatever. This is one that actually suggested a few minutes ago for us to try. 1 over x. We're doing this from 1 to infinity though, so let's go for it. This seems like we're getting good at this, right? Just for fun, let's use a different letter. Pick another one, Justin. B. Okay, all right. That's it's cool. We just want to prove that there's nothing special about A. Okay. This seems like really we're doing well here in terms of how do we know how to approach these. In fact, the integral I've given you here is an easy one as well. No use of substitution, no crazy techniques. What do you get, of course, for the antiderivative?
ln x.
Good, and we can even say ln x, not absolute value of x. Why? Because all of the support that we're integrating over is positive. Yeah, 1 to infinity, those are all positive real numbers, so we don't have to worry about that. So we get ln b minus ln 1, and all of us know that ln 1 is, of course, just 0. So we really just have this question on the table. What's the limit as b goes to infinity of the natural log of b? And the answer is... All right, so we have finally our very first integral that diverges that we've seen today. We just want to make sure we understand that that happens. In fact, it's very special if one converges at all. Really, you might be lulled into thinking like, well, you could always do this. In fact, it's very rare that you could do this. More often than not, if you were to integrate something, just some function off the street, you probably would diverge if you tried to integrate it all the way to infinity. So that was us showing you that it diverges. Right. So what's the issue with this one? This doesn't look like it's an improper integral. Why does this belong in the lesson? I hate the fact that these titles are up here. Oh, wait, what's infinity about this one? Do you see? No, that was. Did you? You were going to say that though? Okay, we'll give you both credit.
I was going to say it more polite.
He read the board. Yeah, do you see what the danger is in integrating across a vertical asymptote? But in some sense, it feels just like what we've been doing. It's the same kind of issue. We're collecting, if you're thinking about an integral as collecting area, we're collecting what feels like could be, we're not sure, in like an infinite amount of area possibly. So we have to be a little careful about this. So you need to recognize where the vertical asymptote is. For this one, it's where? 0. And then you need to apply the same idea. We're going to take the limit this time as, I guess we'll use a again. But this time, if 0 is the problem, we're going to put that there. And our limit needs to go towards 0, and maybe we want to even be more precise, from the right, just to be precise here. We'd like to approach 0 ever more closely. And isn't that what you would do if you were to try to approximate this using f and n? Wouldn't you be like, well, my calculator might not let me do like 0 and 1 as the limit integration here. But what I could do is like use 0.0001, something very close to 0 on the right. And what I would get is like a very good approximation of this integral if I was using f and n. So that's the same kind of mentality we have as we approach it symbolically. What's the antiderivative over here? That's x to the negative 1/2, so that's what? X to the 1/2 times 2. Does that work for us? Check my calculus. Take the derivative. Yeah. Okay. And then we'll eventually we want to plug in 0, but let's try here. So we have 2x to the 2 minus 2 root a, I guess, whatever, or 2a to the 1/2. So this one's not too bad, of course. What do we get? As you plug in 0 for a, we just get 2. Again, the instruction is the same, yeah. Did it give you 2? Good, yeah. Your calculator is using an approximation, so that's good. Math works. Notice the instructions here are the same. That means on a problem like this, it's very easy for this limit at the end to be a number, or maybe not, and it diverges. So either thing can happen on these as well. What's the problem with this one? Thank you for reading. Go ahead, Jackson.
There's a vertical asymptote between poles.
Oh, wow. How'd you know that?
Division.
Where is it? Let's be precise.
1.
Yeah, good. I'll give you even more credit now. And 1 is, in fact, in between 0 and 3. Well, you kind of see where this stuff has been going. What do you think we're going to do? Yeah, just do 2 of this problem, right? So we'll integrate from 0 to 1, the problem spot. And we'll integrate from 1 to 3. And we'll treat each of these problems just like we did the last one, 2 separate problems, right? So over here we have the limit as a goes to 1 from the left of 0 to a, x minus 1 to the negative 2/3 dx. And over here, the limit as a goes to 1 from the right, a to 3, x minus 1 to the negative 2/3.
Why negative? Oh, got it.
I just decided that because I'm about to integrate it, I just wanted to think about it that way. So see if we can get this one off before the bell rings here. So what do we get there? What's the antiderivative? We get x minus 1 to the 1/3. We need a constant in there maybe though. Do we just need a 3? Does that work? Chain rule, nothing really needs to happen with the chain rule, so check my calculus. Okay, and over here, we get the same antiderivative, of course, but we have a different limit and whatnot. It's minus 1. No, hurry. So what do we have here? We have 3 times a minus 1 to the 1/3 minus, what does that all come out to be? Just, if you plug 0 in?
0.
Well, not quite. 0 minus 1, what's negative 1 to the 1/3? I think it'll be a negative 1, then times 3 will be a negative 3, but we're doing minus, so, all right, we're good with that. It's a plus 3. And over here, we can say similar things. We get 3. Sorry, I said that wrong. What happens when you plug 3 in? Help me out. Not something nice, is it? Is it? In the end, it doesn't really matter that much. We'll see. But 3 times whatever the cube root of 2 is, plus minus. An expression involving a. And then the big question is, in both of these expressions, what happens as you take out the limit? As a goes to either negative infinity or negative 1 from the left? Tell me what you get there. Can you plug in 1 in now? Yeah. I'm running out of room here. So what does this come out to be? 1 minus 1? 0, and so who cares? So we get 3 over here for that whole thing. And over here, we get 0, so we get 3 times the cube root of 2. So this finally equals 3 plus 3 times the cube root of 2, I guess. You gonna check us on that too, Jack? Again, tell us whether we got it right or not. type this in your calculator, do F in it, and see if you get the same decimal approximation maybe. Okay? Let me pull up RBC, but let me also, we missed one. We missed one problem. I'm gonna put, we'll maybe put, I've actually got, this problem I'll put on the board just now, and I've got one other one I wanna show you too.